This is part 6 of the series Right Triangles and Trigonometry, and in this part we're going to begin by talking about a concept called geometric mean. Now before we discuss what a geometric mean is, let's take a look at this proportion in a little greater detail. The first thing we need to understand is the fact that each one of these positions in a standard proportion has a name. This is the first proportional, the second proportional, third, and the fourth proportionals. The first and the third proportionals are called the extremes. The second and third are called the means. And so when we deal with the geometric mean, we're talking about the means being the exact same value. So you can see that n and n are the same number here. The extremes are potentially different, but the means are going to be the same when we have a geometric mean. So the geometric mean of two positive numbers, a and b, which are the extremes, is the positive number n that satisfies this proportion. And if we solve for n, we can see that the square root of the product of the extremes is the geometric mean. And so that's the concept of geometric mean. Now let's take a look at it in practice. In this first example, we want to find a geometric mean of 7 and 13. Now the way to solve a geometric mean problem is to establish a proportion. The numbers that we're looking for, the geometric mean, we don't know. So we're going to create a variable, x. We'll just call it x. The geometric mean always goes in the second and third proportional positions. The extremes, the values that you're given, go in the first and third proportional positions in this particular case. Now we go ahead and solve it. We know that 7 times 13 equals x squared, and then the square root of 7 times 13 equals x. And so our value is going to be approximately 9.5. Now you can clearly see that both of these numbers are primes, so this radical is not going to simplify. So we only have one choice. We can either use the square root of 91 or get the approximation, 9.5. In the next example, find the geometric mean of 28 and 8. Again, we're going to set up a proportion. So let's put a proportion here. And we don't know what the geometric mean is, so it goes in the second and third proportional positions, and 28 and 8. Again, we're going to cross multiply. 28 times 8 equals x squared, and then we square root both sides. In this case, we're going to come up with x equals the square root of 28 times 8. This is the square root of 224, so we're going to have to simplify that. 224, 2 and 112, 2 and 56, 2 and 28, 2 and 14, 2 and 7. So there are our prime factors. 1 pair, 2 pair, 2 times 2 times 2 times 7 is 14. So square root of 14. So that's 4 square roots of 14. So this is 4 square roots of 14, which is approximately 15. All right, the next problem. Now this one's a little bit different. It says the geometric mean of 16 and what other number is 36. So here they're giving us the geometric mean. We set up the same way. But in this case, we know what the geometric mean is, so we're not going to be using a variable like we did here. The geometric mean is 36. So that goes here. And the geometric mean of 16 and what other number? So one of our extremes is the missing piece. So let's make it that one. And this is our known extreme. Solving this proportion, x equals 36 times 36 is 36 squared divided by 16, which comes up 81. All right, well, that's a brief introduction to geometric mean. And in the next section, we're going to be applying the geometric mean to some more right triangle similarity problems. In this section, we're going to look at a couple of theorems that are going to give us an assist in solving right triangle similarity problems. Rather than have to constantly resort to the similarity statement and finding the relationships between the different sides, there is a couple of known relationships that we can use that have been resolved down to two theorems that are going to make our lives a bit easier. So the first one is called the geometric mean altitude theorem. And it says, in a right triangle, the length of the altitude from the right angle to the hypotenuse is the geometric mean of the lengths of the segments formed on the hypotenuse by the altitude. So it's saying that AC, this altitude, is the geometric mean. Notice it's in the means position and it's the same value of the two segments formed on the hypotenuse by that altitude. So AC is the geometric mean of BC and CD. And here you see BC and CD. The second theorem is the geometric mean leg theorem. And it relates the legs of the right triangle to segments on the hypotenuse. And it says, in a right triangle, the length of a leg is the geometric mean of the length of the hypotenuse and the segment on the hypotenuse adjacent to the leg. So let's take a look at the first one. Here, BA, the leg of the triangle, the leg of the big triangle, is the geometric mean. Notice it's in the means position, BA, and it's the geometric mean of the entire hypotenuse, the length of the hypotenuse, BD, which is made up of BC plus CD. So BC plus CD is the entire hypotenuse, and the segment on the hypotenuse adjacent to that leg. So this segment is adjacent to the leg. This segment is clearly not adjacent to this leg. Switching to the other leg, AD, AD is the geometric mean, here it is in the means position, of the entire hypotenuse, BC plus CD, there it is there, and the segment on the hypotenuse adjacent to that leg, CD. So CD is adjacent to this leg. To verify these theorems, we only need to go back to the similar right triangles theorem and look at our similarity statements. So let's go ahead and bring up a similarity statement. And here we see ABD is similar to CBA, which is similar to CAD. So these three triangles are similar. We're going to use that to recreate this proportion. Since we have no numbers, we're just going to use these two triangles because they both share an AC and they both have segments on the hypotenuse. So we're going to use this triangle and this one, which is CBA, this triangle, and CAD. Let's start off BC. So BC in this triangle is to, so that's the first two letters, CA in the bottom triangle. So that's AC or CA. Go back to the original triangle and we need AC here. So AC, and AC in this top triangle is the first and third, which corresponds to CD in the bottom triangle. And you can see with a valid relationship here, we've recreated this proportion. Now we can do the exact same thing with these. In this case, using this, we're going to use this triangle and the big triangle. So to recreate that, we'll use the big triangle and the top triangle. We need BC plus CD, and that's actually BD. So we can just put BD and BD in the big triangle corresponds to BA in this little top triangle here. So BA, as, go back to the big triangle, and we need this leg, BA. So BA in the big one here corresponds to CB in the little one, CB. And you can see that we've recreated this. BD is BC plus CD, so that's what this is. And so we've recreated that statement. The same thing would be true of this. We could recreate this time using the big triangle and the bottom triangle. So this triangle and this one. And to do that one, we would have the whole hypotenuse, again, BD, and BD in the big one here is to AD in the little one, so AD. Go back to the big one, and we need this side, because this is the leg that we're looking for in the geometric mean leg, so AD. And AD in the big one is the first and third, which corresponds to CD in the little one. And so there again, we've recreated the same proportion. So that's where these proportions, where these theorems come from. And it's not a formal proof, but it's good enough to show you where this stuff comes from so that you know how to use it. And the key here is that we didn't really have to use either of these two formulas. I would not recommend always going to this because, as you can see, it's kind of time consuming. It takes time to come up with your similarity statement and then to constantly do your preparation. And you'll see in the next few examples how much easier life gets when we use the geometric mean altitude and geometric mean leg theorems to solve problems. In this first example, we're given an altitude, this what we got to find, and we're given the hypotenuse of the big triangle broken down into two segments. Now this is a classic signature for the geometric mean altitude theorem. And so that's what we're going to use, is geometric mean altitude to solve this. Now we know the geometric mean altitude theorem says that the altitude is the geometric mean of the two segments formed on the hypotenuse by the altitude, 5 and 14. So 5 times 14 equals x squared. The square root of 5 times 14 equals x. X equals the square root of 70, which doesn't simplify, and that's approximately 8.4. So that's the first problem. In the next part, we'll continue working on more of these examples.